So I'd like to spend about 2/3 of the time on giving a tour of what I think has become precision comparisons between measurements and computational work. And this will be a little bit fast but I'd like to give you a flavor. And then I'd like to, at the end, tell you about something new that I hope to get people's thoughts on, a new type of system. So because this is a broad audience, many people work on bulk systems. I'd like to start out with introducing quantum dots and telling you what kind of system we're working with. So quantum dots are little boxes of electrons. Imagine just one electron per box, but it could be some small integer number that are trapped in a small region of a semiconductor. In this case, you can see there are 3 boxes that are trapped next to each other with control of their coupling and control of the energy of electrons on the box and number of electrons. And quantum dots have evolved into systems that people use for simulating model quantum systems. This is an example of a small Hubbard model, for example. They're looking at Kondo effect, 2-channel Kondo effect, and maybe building towards trying to make large chains or arrays to connect more directly to bulk systems. Sorry, so quantum dots are made using semiconductor structures where we have a very clean and electronically simple 2D electron system, and then it's effectively carved up into little pieces by electrostatic voltages on electrodes that form potentials. And here's an example of the sort of Hamiltonian we're looking at, and you can see that it tends to look like an Anderson Hamiltonian. So when we measure these systems, often what we do is transport. We measure the current that flows from one side of the other to the quantum dot by tunneling onto and off of this dot. And that current can generally only flow when the number of electrons on the dot can fluctuate, when energy level is degenerate with the Fermi level in the leads. And then you get a sharp peak in conductance, and other times no current can flow, which is called Coulomb blockade. So this is the case where the tunnel rate is very much smaller than the charging energy on the dot, but we can also increase the tunnel rate, and then things change quite a bit. And it turns out that for odd number of electrons on the dot, this is, as I said, an Anderson Hamiltonian. The system behaves as if it's a magnetic impurity coupled to reservoirs, and this idea was introduced by theorists more than 3 decades ago. And I took this on as something to try studying in my PhD. I didn't believe that it was going to work, but I figured, we were going to go into some new regime, and remarkably, it certainly behaves like an Anderson Hamiltonian. So one way to see this starkly is if we look not just at changing the number of electrons on the dot, which is the horizontal axis, but also the energy of injection, where we're looking basically at a spectral function. And you can see that there's a peak in the spectral function, 0 energy. I think you're probably familiar that that's something that shows up as a signature of the Kondo effect. So once we had seen this effect, the next thing I wanted to do was to check to what extent does this quantitatively compare to the available theory, both analytical and at that time mostly NRG. And so one thing you could look at is what's the conductance as a function of temperature, where the 2 quantities are scaled, the temperature scaled by Kondo temperature. And you can see that there's a quite nice match between the solid curve, which is a calculation for NRG in the Kondo regime, and the data. And for those of you who tend to think about bulk systems, I should mention that this looks very much like what you'd see for resistivity in the bulk system. Here it's conductance, and in both cases you're measuring the density of states at the Fermi level. So once we see this behavior, now we can extract the characteristic energy scale, the Kondo temperature, and we can ask, for example, how does that Kondo temperature change when we change the Bayer parameters of the system, the depth of the level below the Fermi level, the tunneling rate. And here I just want to make a point that's distinct from a lot of what we've been hearing this week, which is that what I'm aiming for, and I basically ended up feeling I can be greedy about this because it worked well at the beginning, is to say, here's a case where we know the Hamiltonian, we know all of the key parameters of the Hamiltonian, and for most of them, we can actually tune those parameters. And we can ask, let's not be satisfied with doing fitting, but rather saying, how does, with no free parameters, how does, with everything independently measured and tuned, how does computational theory match to experiment? So one thing that you might want to do there is to look at Haldane's scaling theory from decades, even then was decades old, which said that the Kondo temperature strikingly should be exponentially sensitive to the bare parameters of the system. It should go as in these terms, it should go as e to the minus pi times the depth of the level over the tunneling rate. And so we check, and this is on a log scale, we vary the depth of the level, for example, and you can see indeed it varies exponentially. And if you considered this a measurement of the value of pi, we wouldn't do quite as well as the ancient Egyptians. We get 3.04, but it's really striking that it not only varies exponentially, but it's quantitatively matching. And then you can get even greedier and say, well, Haldane said what the prefactor should be for that exponential. There should be a characteristic energy scale that should be roughly geometric mean of tunneling rate and the and charging energy, and that actually even works semi-quantitatively. So it's really striking how well this works, and I hope that leads this kind of system to have a distinctive role in benchmarking theories, which I think it has for NRG over the past 2 decades. All right, so Kondo effect, even 2 decades ago, was by experts at least quite well understood. Can we see systems that have either richer behavior to drive what the limits are in computation and do comparisons, to see more kinds of exotic behavior, and maybe even make connections with materials. So, so one thing that here was something where we set out to build a particular system, and though it surprised me, we succeeded in doing that. Here we were inspired by saying, well, let's build toward real systems. Let's take the next step and have 2 impurities coupled to each other. So if you're familiar with the 2 impurity Kondo Hamiltonian, that's going to be a thread through some of the rest of the talk. And so we said, let's have 2 quantum dots next to each other. So we have now an interdot charging energy. So when we put an electron on one dot, it affects the other. And initially we intended to have tunneling between the 2, but as you'll see, we ended up getting rid of the tunneling and still seeing something interesting. So we can separately measure the conductance through each of these dots. And then just to see what happens when you have 2 dots, you can imagine you use 1 gate voltage to tune the number of electrons on one dot. And so you can change it from n plus 1, n plus 2, and so on. And you can use another gate voltage to tune the number of electrons on the other dot. But in fact, each of these capacitively couples to the other. So these become diagonal lines. And then because of the interdot charging, you can't add 2 electrons for an infinitesimal cost in voltage. So we also have to take that into account. And this is what, on a cartoon level, you would expect to see for the stability diagram. So we can label this by the occupancy that you'd see. We're going to focus on this case where we have 1 extra electron, but it can sit on either site. So this is the cartoon picture. Let's see what the data look like. Here are the data. They bear a passing resemblance to the cartoon. And the reason that I'm showing you this, and I like this plot, but also it really illustrates that we can extract all of the parameters of the system with almost no uncertainty. And so, but this is a sort of boring case where there's weak tunneling to the reservoirs. Let's now introduce more tunneling. And when we do that, we see that this region where we have that 1 extra electron has enhanced conductance. I should actually just go back for a moment. You notice that there's no conductance in this region. And the reason is that you have 1 extra electron, but it's trapped on the 2 sites. It can juggle back and forth between the 2, but can't get out. However, at these corners, an electron can come from onto one site and then come off onto the other, off from the other site, for example. So these are called the triple points, and we'll hear more about them going forward. So, so seeing conductance in this region is not something you'd expect in a simple picture. It turns out that's a Kondo effect that's enhancing that conductance. And in fact, it was first observed by a group in Germany before this, and we studied it in more detail. So what turns out to be happening there, I'm going to skip quite quickly, but what turns out to be happening there is that we have a degeneracy both of spin and of site index. So there are 4 states, and it turns out even though the Hamiltonian does not have fourfold symmetry, does not have the full symmetry of those 4 states, there's an emergent symmetry that is SU4, that's the maximal symmetry of those 4 states. And that gives you the Kondo effect here. So if you look at the degeneracies, let's pick a location where we have 1 extra electron. It can be on the left site, up or down, the right site, up or down. And then if we take the NRG results that are from Gerge-Zerand and co-workers, you'd predict that there would be a 4-fold periodicity as you're adding electrons, not a 2-fold periodicity, and that there would be a difference between, yes, the first electron and the second electron added. And so if we map out this space and focus on the lines between the triple points, and specifically the ones that have 1 extra electron, not 2, you'd expect a picture like this, where you have higher conductance right next to where you have 2 electrons on the double site, and lower conductance where you have 0. And so we can look at the data, focusing on the lines between the triple points. And if you look at them, there's nothing that really jumps out in terms of asymmetry, but we can saturate the color scale, focus on just the peaks. And now you see that with the exception of this one case, all of them have this even-odd behavior, and therefore the 4-fold periodicity. So really there does seem to be this, this full symmetry of the system. And now we can say, all right, let's turn on a magnetic field, a Zeeman field, and see what happens to this. And we should still have Kondo effect in this region, but we should destroy the spin degeneracy. And indeed, here's what you see. You lose this 4-fold behavior and it goes back to 2-fold. So we might want to go further and try to do more to establish agreement between the simple theoretical models and experiment. If we do this, you can see, all right, here's behavior in experiment, here's NRG calculations. I like color plots, but I like to say that they can hide a multitude of sins. So let's go to line cuts. And here we have, at different temperatures, the data and the NRG calculations. And again, this is no free parameters. We've measured every quantity in the bare Hamiltonian. And you can see that it matches really quite well as we change temperature and tune the number of electrons in the system, or the level below the Fermi level, until you get to quite low temperatures. And we still do not understand why at 30 millikelvin there's not a good match. We have other reasons to believe that our electron temperature is 20 millikelvin or below. So there are some mysteries, but I think that the strong match allows us to actually push on and take seriously when things don't match. So here we can compare the data to an NRG calculation for conductance versus temperature. You can see it's a pretty good match, but how good is that? We can also put in this dotted, I think, green line, this is SU2 Kondo. This is the standard Kondo that comes from Anderson model. It clearly doesn't match. Actually, strikingly, an SU4 Anderson model maybe even matches the data better than the microscopic picture that we created. So, so now I'd like to very briefly touch on, not really explain, but touch on how we can get quantum criticality and non-Fermi liquid states in a quantum dot. And so this is something that people have been exploring with various different kinds of systems, motivated by the kinds of bulk systems that many of you are measuring and modeling. but also studied in these nanoscale systems. And so I think you're familiar with the idea that if you have two different competing ground states in the system, tuned by which one is the ground state is tuned by a parameter, you can go to the point where neither is the ground state. And then remarkably, as you raise the energy scale or temperature, you have fluctuations that occupy a broader and broader range of this parameter. So instead of being a curiosity that occurs only at 0 temperature, can actually have important consequences at high energies. So, so what I'm hoping to show you here is, I think, the first case where we can take a system with a known Hamiltonian, known values of all the parameters, and actually compare quantum critical behavior to between experiment and computation. So specifically the two-channel Kondo effect, a spin that's coupled to two different reservoirs antiferromagnetically. We can take a cue from an old movie, Office Space, in which an employee needs to satisfy two bosses. And of course, it's impossible to do both of those. So we can ask, what is the space of quantum critical behavior in the system? And there are predictions for what should be the crossover between one ground state and the quantum critical region and the other ground state in the quantum critical region, specifically this parameter T star that tells you, I'm sweeping some things under the rug, but that tells you that crossover. And the control parameter is the difference in the J's coupling to the two reservoirs. But in our case, we know what the relationship of the J's is to the bare parameters of the system. Yuval Oreg and I spent years trying to figure out how to create an overscreened system like this. And I'm happy to talk for the experts about how we actually do this. But the bottom line is we build a system that should show two-channel Kondo effect with tunable coupling to the two channels. And so here's just a fun picture of, this was a non-trivial thing that to make. One of my students joined me when I was on sabbatical at the Weizmann Institute and spent 6 months figuring out how to make these fancy things. All right, so we're going to try to probe not only the quantum critical region, which we had done in earlier work and seen non-Fermi liquid behavior, energy to the 1/2 rather than energy squared, but actually map out this whole space. And so here's what we do. We take data, we extract what is T star in this system as a function of gate voltages that tune the energy levels of the system. And you can see, we can find the quantum critical point, and we can see that T star rises, and it rises quadratically but asymmetrically on the two sides of the quantum critical point. Remarkably, this is directly echoed in the NRG calculations. Again, I think that in the color scales are just arbitrarily scaled, but otherwise there are no free parameters here. So to summarize where we've gone so far, we've done some pretty detailed calculations of many body physics in a quantum dot, a double quantum dot, and a system that shows a quantum critical point, a quantum phase transition, and tried to increasingly rigorously challenge the state-of-the-art calculations. Up to now, this has been primarily NRG, but part of why I'm here is that I'm really excited about the prospect of opening this up to a broader set of techniques, which might have advantages in different cases, for example, extending to a lattice or going out of equilibrium. So now I'd like to tell you about what I've been preoccupied by lately in this space, which is another attempt to try to get a two impurity Kondo. As you may remember, we didn't quite succeed the first time. So it turns out that it's rather difficult to build a two impurity Kondo system out of quantum dots. Part of the reason is that if you allow charge to move from one site to the other, you, as some of the people here actually elucidated, you blur out the quantum critical point, which is actually mathematically closely related to the critical point in two-channel Kondo. Gergely-Zarand and co-workers found a way to ameliorate this by adding 2 extra quantum dots as a bus to sort of talk between the original dots, but this would be very difficult to scale to larger systems, and I'm really inspired by the idea of trying to get to lattices. So is there an alternative for doing this? And a few years ago, I learned about something that was a quite exciting alternative. So, so in around 1990, Kostya Matveyev pointed out that if you have a metallic grain, something that has a continuum of energy levels, but a finite charging energy to add an extra electron to the system, if you have a metallic grain coupled to a lead, that you can actually get a Kondo effect. And here it's an interesting mapping. The charge on the grain ends up playing the role of the local spin. The screening reservoir is a little more subtle, and I'll come back to that since we're going to try to address this model. So, so here's the Hamiltonian. I'm not going to go through it in detail, but notice this is 3 decades ago, and after some early efforts, not much happened experimentally. Why was it hard to do it experimentally? Well, you have some pretty stringent requirements. You want a large charging energy, which means it needs to be a small site, but you also want a large density of states in the grain. So it's hard to do this with a semiconductor. You need precise control of tunnel couplings. So if you say, okay, I'm going to use a metal in order to achieve this, then it's hard to get one channel coupled to it with transmission between 0 and 1. Instead, you'll get a million channels with very tiny transmission. So semiconductors or metals alone can't do this. And so a few years ago, Frederick Pierre, who's now at Saclay, had a very clever idea, which was to use the best of metals and the best of semiconductors. He made a metal grain that was intimately coupled to a high quality 2D electron gas in a semiconductor. So one could control the tunneling into this grain using quantum point contact gates, but have a significant charging energy and effectively 0 level spacing. So, and by the way, the modes that couple to this, he used quantum Hall edges, which are particularly perfect and controllable 1D states. And he was able to show that if he attached 1 lead, he got Kondo effect, 2 leads, 2 channel Kondo. And this figure shows that if he tunes the 2 couplings separately, that when the 2 are equal, you get a maximum conductance through the system, and that's reflecting the 2 channel Kondo fixed point. He even went to 3 channel Kondo with 3 leads and showed a really amazing recapitulation of an RG flow diagram just from experiment, showing that you have a 3 channel Kondo fixed point, you can flow to the 2 channel Kondo fixed point, or you can flow to the strong coupling fixed point down here. So it's quite amazing that as you tune these different couplings, you can really understand what's going on. All right, so so I thought, well, this is a great Kondo site where every one is going to be identical to every other one, and you can really tune all the parameters the way you want. And so I thought, let's make 2 of them and make 2 impurity Kondo. And then that started a saga of 2 to 3 years of interacting every few months with Frederick Pierre and saying, we're stuck, we have this problem. And he said, oh yeah, I ran into that. So we succeeded in reproducing his single site behavior and then extending now to 2 sites. And in talking with Andrew Mitchell, a theorist, he pointed out that the Hamiltonian isn't exactly the one that we thought it was going to be. So, so in fact, when you have coupling between the 2 sites, you not only have a spin flip, but also a tunneling event. And I'm happy to answer questions if you have them later, but it doesn't look quite like 2 impurity Kondo, but actually it has even a richer phase space. And so what we're now going to do is measure conductance from 1 lead through the 2 sites into another lead and tune, let's say, fix the coupling to the 2 leads and tune the coupling between the two sites. So we see again this kind of stability diagram. We're again going to go to the triple points, which is And strikingly, Andrew calculated that at the triple points, one should get an entropy of 1/2 log 3. The log 3 makes sense. There are 3 states you can go between. The 1/2 is reminiscent of what you get from Majoranas. And so that's striking. We should get a conductance of 1/3 through this system because there are 3 1D channels that we need to go through in series. And as we tune the relative couplings to the leads and between the sites, we should get a maximum in the conductance. And so, so I'm just going to, we pick the right place to look. And then we, for each coupling to the leads, you can't see the value here, but it's 0.9 there. We tune the coupling between the 2 sites, and you see there's always a maximum in the conductance at that point roughly where the 2 are equal. And so as you change the coupling lower and lower, sorry, the conductance to leads lower and lower, that maximum moves to lower values of coupling. So, so we had hoped that we might be able to study the Kondo quartet model. Instead, it's something maybe even richer, and we're now trying to push up the energy scales in the system by moving to a new material system. So with that, let me thank you.
Thank you. Thank you very much. We have time for questions. Please, can you repeat the question?
I will do that, yes.
The last part, is there any subtlety in the coupling of the edge state to the metal grain?
So Harold asked, is there a subtlety in the coupling of the edge state to the metal grain? And the answer is absolutely. And in fact, I would say I don't necessarily fully understand it, but let me step you through it. We have the edge state. In fact, this is typically a filling factor 2 quantum Hall system that we use this point contact to shrink down to 1 mode with controlled transmission. So we have from 0 to 1 e²/h through this constriction. And then it's very important that when it hits this island, this metal grain, it has to have basically 100% absorption in the grain. So we're sort of at the 99.9% level. But I think I still don't fully understand, you know, I've thought of these little loops of edge modes as being part of the metal grain, but I'm not sure that's quite right.
Other question? Yeah.
So how do you have scalable? You can do more and more of these. So what is your long-term perspective?
Yeah, so thanks, Jan. I didn't say fully, but I've for a long time dreamed of making chains of quantum dots. You know, you could say, well, maybe it's hard to make 100 quantum dots. At this point, it's easy to make 100 quantum dots. It's hard to do the electronics to be able to tune all of them. What's really hard is knowing that you've tuned each of them correctly, and then that they all have the same energy level. And even if they do, each one will have different quantum states. So it's going to be hard to make a completely uniform chain. So my hope was here, every island is basically identical to every other island in the ways that matter. And so I'd like to be able to go to a 1D chain, maybe even a 2-leg ladder. And I've just recently been thinking about, because the Kondo screening actually occurs in part in the neighboring grains, maybe one can even make a 2D lattice of these and just have metal grains connected by quantum Hall edges. And so my dream would be making a 2D lattice, and ask me again in 10 years, and hopefully we'll be at the 1D chain.
Is it possible to apply pulses, strong pulses?
So the question is, can you study dynamics? The answer is yes. People have done it more using single frequency AC modes. An example would be take an energy level that's below the Fermi level and wiggle it up and down, and wiggle it so that Kondo effect at your temperature is strong for one extremum of the sine wave and is weak at the other extremum. If you wiggle slowly, you'll see Kondo effect half the time, and therefore if you measure conductance, you'll see significant enhancement of conductance. If you wiggle it fast, there's no time for the Kondo screening cloud to form. So yes, you can do pulses, and I'd be happy to discuss it, but the easier thing is doing AC excitation.
Okay, unless there is a very pressing question, I think it's time to move on, and
Thanks.
thank David again.